So we're going to start with vertical motion. Who is in physics this year? Okay. So you have to do it the calculus way, even if there are other ways that you learned it in physics. Okay, you need to learn the calculus connections here. So when we're talking about an object that's in vertical motion, going up or down, okay, or actually it could also be straight sideways. Well, this is for vertical. This position function is often in calculus defined with a variable s. I don't know why, s to t. And it looks like this. Okay. And some bits of information that you need to know is that t is time in seconds. These are little zeros. Okay. Time in seconds. All right. S is position. And that's in feet. From the reference, which is usually the ground level. Okay? These are your variables. And so X and Y, it's T and S. Okay? And then there are these things right here with the little zeros on them. V sub 0 and S sub 0 are initial values. This is the initial velocity. And this is the initial position. These are constants. These two right here are variables. And these two are constants. All right. Just a rule aside right here, I think y'all probably already know this, but when we say initial, that means time is 0. Okay, that means if t is 0, these are our initial values. Okay? All right, so I am going to take the derivative of the position function. Remember, v sub 0 and s sub 0 are initial values. Oh, I forgot to say, some textbooks use little i's for initials, so they say vi and si. Has anybody ever seen that anywhere? I don't know which one y'all use in physics this year. But it's the same thing. It's the initial value. All right. So the derivative of this isolated polynomial function. What's the derivative of negative 16t squared? Negative what? Okay. What's the derivative of 2t? T. What's the derivative of 7t? 7. What's the derivative of 12t? 12. What's the derivative of v sub 0t? V sub 0 or v naught. Okay. And then you can okay. So what we're going to talk about today is what does this mean? You take the derivative. All right. So I'm going to take this back to the other notation. Instead of s prime, I'm going to see ds dt. Although s prime is fine. What are the units on changing position? Feet. What are the units on changing time? Seconds. So what are the units on the derivative of position with respect to time? Feet per second. Does everybody see? All right. What it turns out is that the derivative of position is velocity. Tells you how fast the object is moving. Okay? Velocity. I'm just copying that over again. All right. Now I'm going to take the derivative of velocity, which is the same thing as taking the second derivative of position. What's the derivative of negative 32t? Negative 32. And what's the derivative of v0? 0. So here is the second derivative. And let's think about what the units for this would be. It would be the units for velocity. What are the units for velocity? No. In this problem, it's feet per second. Divided by what are the units for time? second. And I also did this in one place, so you all remember what feet per second is the same thing as feet per second squared. Feet per second squared does not have an intuitive feel for what it means, but people use it all the time, or meters per second squared. Feet per second gives you a better feel for what's changing. How is the velocity changing? So many feet per second every second. So we use either this or this for our units. And hopefully you recognize what this is the unit for from the physics studies when I say, what is it? Okay, so acceleration is the derivative of velocity. All right, which is the second derivative of position. And for this vertical motion, it's negative 32 feet per second squared. In science, they use S, but a lot of math textbooks use SOC. Either one of those is acceptable. This number right here is the acceleration due to gravity. And it's considered a constant when you're working at the level that we are. In reality, it can change a little bit. If you're like at the top of the mountain, it's a tiny bit different than it is if you're at the bottom of Death Valley, okay? But it's treated as a constant. When you're working in the metric system, we use a different number for the acceleration due to gravity. And you should recognize this from physics.
Please excuse the interruption. If you would like to meet with the college representatives of Queen's University of Charlotte, please go to the group room. If you want to see the representative from Queen's University, please go to the group room.
The position would be using the constant negative 4.9 instead of negative 16. And the velocity, when you take the derivative, ends up as negative 9.8 times t, and the acceleration ends up as negative 9.8. And I think in your 9th grade physics you used negative 9.80, didn't you? That's one you use all the time. Okay? So they're the same thing. There's absolutely no difference in the two of them. One of them is the metric system, and one of them is in whatever we call our system. Okay? All right? If we got this, you need to pay attention to which one you're using. All right? We'll work out the problem in a minute. Let me just give you some samples of some given information. We're going to take objects and tell you some stuff about them. If I tell you that an object is dropped from a height of 40 feet, if that information is given to you, you've got to be able to convert it into the language that we are using, the variables that we are using. Okay? So, dropped. Is it right the instant before I let it go? How fast is it going if I just say I drop it? Zero. Okay? So this information, its velocity is 0. Okay? And if I drop it from a height of 40 feet, I'm telling you where it started, so the initial position is 0.
What would be 40?
It would, because that's the wrong answer. The initial position is 40. Sorry, because I looked ahead to the next problem. Okay? Initial position is 40. All right? And you know, in science, they make you put units on, and in math, they say just make sure your units are all good and don't worry about it. Shot up from the ground that. Let's look at 150. Shot up from the ground at 150 meters per second. Okay, so we're going to start on the ground. That is, initial position is 0. And at the beginning of the time of interest of this problem, how fast was it going? 150. That's initial velocity is 150. Or is that the speed of so there's a difference in, I don't want to drop this because it's expensive. If I just let go of it versus if I go like that and let go of it. Yes? Okay, one of them is drop, the other one is thrown down. Okay? So the two pieces of information in here is that it starts at the top of the building. So what is that piece of information? That's not S of 0. Okay? And what is this piece of information? B sub 0. And if you're not careful, you'll get this wrong. By convention, things that are moving up have a positive velocity, things that are moving down have a negative. So you have to put this into that convention and tell me the initial velocity is negative. Everybody see? So from any of these three problems, I have given you the initial velocity and initial position. So I'm not going to do this for all three of them, but for this third one, from this information, you could write those three equations. All right? So what would the first equation be? Position is, what are we in? Are we in metric or English? English. English is the speed. So we need the one that starts with a 16, yes, not the one that starts with a negative 4.9, okay? Negative 16 t squared plus, instead of v sub 0t, we write, actually I'm going to change that to minus 25t, here's my v sub 0. And then plus 300, here's my s of 0. So do you see how you could do that for all three of those problems? Yes? Okay, once you have the position, once you know what the position is, you can tell me what the velocity is. The velocity is the rate of change of position. How is your position changing? That's called velocity, that's derivative. So take the derivative and you get negative 32t minus 25. And for all of these vertical motion problems, your acceleration is constant, and it should turn out to be either negative 32 if you're in the English system, or negative 9.8 if you're in the metric system. Okay? Now, once you have these three pieces of information, you ought to be able to answer any question I ask you. If I say, where is the object, which equation do you need? Position, velocity, or acceleration? Position. If I say, how fast is it moving, which equation do you need? Velocity. So we're going to go through a couple of scenarios where we're not actually going to solve any of them, but we're going to write down what would be the first step towards solving this answer. And if you can get the first step, then it's really like algebra 2, okay? Certainly if we get to use our calculators, it's certainly not difficult to do. So I'm just going to go through a few things where I might ask you to find something. The position at 2 seconds. Okay? And all we're going to do is write down the notation that tells us what to do. We're not actually going to do it. Okay? So, what would I do? What would you do if I said find the position at 2 seconds? What would you do? S of 2. Take 2 and plug it into the position. Okay? And then grab your calculator and go to 10. Yes?
How would you know which one to do it?
Well, I did 3 examples, but you can only do it one problem at a time, whichever problem. Do you mean which of these 3 to do?
So I mean, the 4.9 or the 16.
Okay, that you're gonna get by, first you're gonna create your equations up here. All right, and how do you know whether you use the 4.9 or the 16?
Since the units.
Right, so, we're gonna assume that you've already written your 3 equations, and then you pick which equation you need to do. Okay?
Like, okay.
Yes. Okay, so this is just for any
The little part of it.
right, any set of 3 equations that you've got. Once you write them down, what do you do with them? The velocity at 4 seconds. V(4), and write that on your paper, okay? If on the AP exam, it's a 2-point answer, you get 1 point for telling them what you're gonna do, and you get the other point for doing it right, okay? So write that, notation on there. Average velocity. Now, this is gonna come up over and over and over again. We're doing the absolute simplest applications right now, vertical motion, constant acceleration. Later on, there'll be some more complicated problems where the same principles will apply. The arithmetic is just a little bit harder. Average velocity has a definition, and you need to make sure you know what it is, okay? I think in physics, they use a V with a bar across it. Does that sound familiar? You're in there now? I'm not real sure where you are. Okay, not a vector, but anyway, the average velocity, in calculus, we don't really use a symbol for it. There's no particular symbol for it, so we just write average velocity, okay? And the average velocity is, you don't compute this from velocity. You compute it from what was its position at the end minus what was its position at the beginning, and you divide that by how long it took. How far did I go, divided by how long did it take me? That's how you guys would compute velocity if you said, oh, I went 300 miles, and it took me 2 hours. So how fast was I driving? Too fast. Okay, 150 miles per hour, that's too fast, okay? So you just, how far did I go, divided by how long did it take me? So change in position over change in time. You don't actually use velocity to get this answer. Okay, but consider what units you get. What are the units in the numerator? Feet or meters, yes, and the denominator of the units are seconds. So everybody see? Okay. So that's how you find average velocity for that says instantaneous. Instantaneous velocity at 2 seconds. I'll write that so you can read it. Instantaneous velocity means the velocity right now at some specific point in time. So for instantaneous velocity, you would do V and you would plug in 2, which is the same thing as saying the derivative and plug in 2. Those are the same thing. Any questions about that one? What is the time required to reach a height of 10 meters? What is the time required to reach a height of 10 meters? Drop something, or I'm throwing something up in the air, something's happening. What is the time required to reach a height of 10 meters? Now, the tricky part is that these questions are in a paragraph with the initial height, and you have to make sure that you pull the initial height separate from what happens after the initial height, okay? But this is a position. This value is a position. So what this is asking you to do is to take the position function and set it equal to 10. When will the position equal 10? Does everybody see? So you're going to get this parabola, this quadratic, equal to 10, and you're going to need to solve for t. Quadratic formula, factoring, any of the methods, use your calculator to graph it, find the answer to this by whatever method seems appropriate. Okay? Time it takes to reach the ground. Time it takes to reach the ground. Okay, what does reach the ground mean? Zero what? Position, velocity, or acceleration? Position. This means position is 0. So you take the position and you set it equal to 0 and you solve for t. Other questions? This is asking you for a velocity, but it's not giving you a time. What is it giving you? A position. Now, in physics, they have created some formulas where one formula will do this for you, all right? I need you to not use that formula in here. What I need you to do is take this position and the only reason I say not do it is because later it won't, the formula that they developed in physics doesn't work in other circumstances. It only works for certain things. And so what we're doing works for everything, okay? So first I'm going to take the position they gave me and I'm going to find the time that it gets to that position. That's first. And then after I find that time, then I'm going to find the velocity at the time that I found. So it's going to be a two-part problem. First, put the position in, find the time, then take that time and plug it into the velocity. So it's a two-part equation, two-part system. Does that make sense to everybody? Yeah? Okay, actually, I shouldn't call this A. This is kind of a different problem, okay? Find the initial height of an object drop, or a dropped object, that hits the ground after 5 seconds. So first of all, a little bit of vocabulary. If I say after 5 seconds, when we say after 5 seconds, we really mean at 5 seconds, okay? It doesn't mean at some time after 5 seconds, it means right at 5 seconds. So in this case, you do not know the initial height. So what is it you're trying to find?
The
No.
SO.
SO, you're trying to find this, okay? So you can start by writing your equations with what you do know. This one is in, it doesn't say what it's in, does it? Let's pick one. Let's do it in, meters, okay? Let's do it in meters. So this would be negative 4.9 t squared plus, do I know the initial velocity? Read the whole problem. Do I know the initial velocity?
Yes.
Yes. What tells me the initial velocity? Drop tells me the initial velocity is 0. And do I know the initial position? And the answer is no. So to put it there. Okay? What would my velocity function be? Velocity derivative of position. And what's the derivative of negative 4.9 t squared? 9.8 t. This is 0. Yes? And this is derivative of a constant is 0. So both of those go away. So, and actually you could leave this out right here and it would be fine. So here are my two equations based on what I've been given. And I know that this is what I'm trying to find. So what else have they told me that I haven't used? What happens at 5 seconds? It hits the ground. So 5 seconds hits the ground. So that tells me that two things happen at the same time. That is telling me that when the time is 5, the position is 0. That's what it's telling me. When the time is 5, the position is 0. Everybody say? Now how does that go? Well, time position 0, negative 4.9, 5 squared, I can leave that middle thing out, plus s of 0 has to equal 0. And I don't even need that second equation, that velocity equation, I don't even need it. Y'all see? Now, can we just put dot here? Okay, I'm going to get out my calculator and compute it, and I'm going to get some answer. Does everybody see? All right, so when you get to these velocity acceleration questions, your goal is to identify what you've been given and work with these specific equations to get the answer, using these different kinds of translations. All right? So for other linear motion, things that are only moving in one direction, not things that are going up and coming back down in an arc, that are bouncing around or a spring, but just things that are only moving in one direction. We need to get a couple of conventions in line. What they mean. The sign of velocity. If I tell you that velocity is 0, then it is not moving, or it is stopped. So sometimes things just stop when they run into things. Sometimes you just, like you roll a ball across the ground, eventually it will stop, yes? But if you throw an object up in the air, it's going to go up for a little while and then it's going to do what? It's going to come down. And what happens in between it going up and going down? What does it do? It stops, okay? It instantaneously stops. So velocity 0 means it's not moving or it's stopped. If velocity is positive, then the convention is that it's either moving up or to the right. That's the way that we have set this up. No particular reason for it, it's just so that we're all on the same page. And if velocity is negative, that means the object is moving down or to the left. These are just the conventions that people use most of the time. Sign of acceleration. If acceleration is equal to 0, I'm going to take it back to freshman year. There's a basic formula that's got acceleration in it. What causes acceleration? Please tell me y'all know this. Okay, if I want to make one of you slide backwards in your chair, what have I got to do? Force. I got to push you. Yes? Somebody say force back there. Okay. So there's this old formula of force equals mass times acceleration. So basically, when acceleration equals 0, that means that force equals 0, and that means that velocity is not changing. It doesn't mean velocity is 0. It means whatever you're doing, you're going to keep doing. Okay? So if you're driving along at 70 miles an hour and no new force is applied, you're going to just keep driving along at 70 miles an hour. Okay? If you're sitting still and no new force is applied, then you're just going to keep sitting still. That's what acceleration 0 means. It doesn't mean you're not moving. Okay? It means you're not changing your motion. If acceleration is positive, that means that the force applied is positive. The force applied is positive means that it is pulling, is it okay if I say pulling? Do you prefer pushing up or right? You can say pulling or pushing, I don't know. I guess pushing is better. You can always, oh, it doesn't make any difference. The force is either pulling you up or pushing you to the right. And it's going to make you change what you're doing. Okay? If the acceleration is negative, it means that the force is negative. And that means the force is going to try to pull down, is pulling down, or is pulling to the left. Okay? And now we're going to put these two things together. And this is where it would be really nice to have a skateboard down here. No, I don't. Okay? Just to imagine me on a skateboard. Whatever that does. And I'm cruising along, nice and steady, nice and steady. And then Grace, the little devil, comes up behind me and gives me a shove. What's going to happen? Well, before I fall, I'm going to speed up. If I am moving to the right, I'm moving right, move right, plus force right. Those two things acting in the same direction result in speeding up. I'm going to go faster. Okay? And I said to the right, but that would apply also if they were both on top. Okay? So what about if my velocity is positive and my acceleration is negative? That is, I am moving right. No, acceleration is negative.
Oh, then you're
So
slowing
our
down.
force is applied to the left. So if this is y'all's right, yes, am I going in circle? So I'm moving along this way, and Grace gets up and pushes me from this direction. Okay? Then what's the first thing that happens before I fall down? I'm going to slow. I may eventually stop, but I am definitely going to slow down. Okay? I may or may not end up going backwards, but the first thing that's going to happen is I'm going to slow down. Okay? So there's two scenarios. We need to get the other two. What if both of them are negative? I'm moving left, plus a force is applied to the left. I'm going that way. Somebody grabs me and pulls. What's going to happen to me before I fall? I'm going to speed up. Okay? And what's the last one? What have I not done?
The less than 0 and 1.
Okay. And in this case, I am trying to move to the left, or maybe down, trying to move down, and the force is applied in the other direction. The force is applied to the right. And once again, I am going to slow down. So, to summarize, if velocity and acceleration have the same sign, If I'm trying to go in a certain direction, and then somebody applies a force in that same direction, what's gonna happen?
Yeah.
Speed up. Go faster. In that same direction. If velocity and acceleration have opposite signs, then I am going to slow down. And I may eventually stop, but I'm definitely going to slow down. Okay? And I just want to apply that just mentally for a couple of seconds to straight vertical motion. This is for linear motion, anything that's moving up and down, left or right, or your diagonal. Okay? Those are all fine, but this, seeing this about in terms of something you throw in the air is, I think, the easiest way to remember it. You let go of something, you throw it up in the air. Which way is its velocity? Everybody point. Which way is its velocity when I throw it up in the air? Which way is Earth pulling on it? So what's going to happen to that thing you threw up in the air? It's going to slow down. And eventually it will stop, called its apex, the maximum. And then it's going to start to go down. And which way is the Earth pulling on it? So what happens as it comes back down? It speeds up. Never mind that it's going down, it is still going to speed up. Okay? So you're going to need this information in order to answer some of the questions about velocity and acceleration. Does that make sense? Yes? Okay. All right, part 2. Oh, I was trying to keep the window, but I think I'm going to give up. I touched on this just a little bit with velocity and acceleration. But I want to give you a graphic understanding of the difference between average versus instantaneous rate of change. Draw yourself a nice arc with a nice curve. What about me, Grace? I say, really nice curve like this. But draw something you can put some notes on. Okay? Draw something you can put some notes on. Mark 2 points that are fairly far apart. And draw a line connecting the 2 points. I'm going to name this point A and this point B. I want to talk about the average rate of change. On average, how is this curve changing? Okay, the average rate of change. And what I'm talking about is the slope of the secant line. That's the line, it's not a tangent line. That connects A to B. It's just slope. Y2 minus Y1 over X2 minus X1. It's not a derivative. It's just the slope of a line. Y2 minus Y1 over X2 minus X1. The instantaneous rate of change at point A. How is this thing changing right here, right now, at this instant? Okay? The instantaneous rate of change at point A. That would be the slope of the tangent line. That would be the slope of the tangent line. So in this picture, which one of those numbers is going to be bigger? The instantaneous rate of change at A or the average rate of change from A to B? Which one of those is going to be bigger numbers? Which is going to be bigger? Oh, look at the two slopes. Which is going to have a bigger slope? The blue line or the black line? Blue line. So the instantaneous rate of change will be bigger than the average rate of change. Does everybody see? Okay, the slope of the tangent line. Now, slope of the tangent line means derivative. That means find the derivative. That's the slope of the tangent line means. The instantaneous rate of change at point B. The instantaneous rate of change at point B. Okay, back up to the picture. The instantaneous rate of change at point B is the slope of the tangent line at point B. Right? There's two different definitions. If I ask you for an average rate of change, do not take a derivative. Average rate of change, just do a y2 minus y1 over x2 minus x1, just a straight slope. Where did I start? Where did I end? How long did it take me to get there? Okay, but if I ask you for an instantaneous rate of change, then I need you to do the derivative. Slope of the tangent. Okay? As a general rule, you can't take the slope of A and the slope of B and add them together and divide by 2 and get the slope of the average rate of change. Does that sometimes work? Yes. Okay? But in general, that's not true. Only in very specific circumstances. Right? In one of your homework problems tonight, I think you'll be better off if you could print the graph out of the book. And so I think it tells you this right there on the page, but there's something called mathgraph.com that will connect you to your textbook and to graphs in your textbook. So if you need to print out a graph from your textbook, go to mathgraph.com. Okay? Okay, so I've got a function from somewhere. F of x equals 3x cubed minus 2x plus 4. Some function. Maybe it means something, maybe it doesn't. Okay? And I took its derivative. F prime of x is 9x squared minus 2. Right? And I asked you to find the average rate of change on 1 to 2. Here's the function, here's its derivative, and I want the average rate of change. How do you say about? I really can see there. The average rate of change of the function. So when I ask you for average rate of change, do I want you to take a derivative? No, no derivative, just slope. So you need basically y2 minus y1 over x2 minus x1. And in this case, that's f of 2 minus f of 1 over 2 minus 1. Everybody see? Okay, and you all see that that becomes just a computational issue. You can do VR calculator, you can just like that. Yes? Okay, if instead I ask you to find the instantaneous rate of change at x equals 1 and then at x equals 2, this is two different answers. What's the rate of change at the beginning and the end of this interval? Or halfway through the interval, somewhere in the middle of it. Then what I'm asking you to do is take the derivative and plug in that number. Both of these say rate of change. You just have to keep straight which one is what. Okay? We're going to pause and take this in and stretch. All right, so back again. Not too much longer now. Suppose I have a function, and instead of calling it f of x, I call it c of q. All right, instead of f of x, it's c of q, and c stands for cost. Maybe it's in dollars, maybe it's in thousands of dollars or something. And q stands for order size. How many did you buy? How many did you purchase? How many did you purchase? Just a number, okay? All right? So this is a problem that's in context, and that means that your answer has to be in context, and that means you get better. All right? So if I ask you to find the cost when 200 items are ordered, find the cost when 200 items are ordered. We're not going to actually work these again. We're just going to set them up. What am I asking you to find? What am I asking you to do?
Y equals C.
C, evaluate it at 200. I'm telling you, go to the cost function and plug in 200. Yes? I showed the freshmen these little code marks. They got all excited. What's the cost for 201 items ordered?
C is
201. Same question, right? Just plug in a different number. Okay? If I ask you, what's the change in cost when Q is increased from 200 to 201? What's the change in cost when Q is increased from 200 to 201? How much is the cost? Anyone ask you to find the change in something? What operation is that always? Subtraction. So this is asking you to say, find the cost of 201 and subtract the cost of 200. So I might skip over the first two questions and go straight to the third question, right? It requires you to do the first two questions. What is the average rate of change in the cost? The average rate of change in the cost as Q goes from 200 to 201. Average rate of change. So, slope. Yes, that's all it is, a slope. We don't take a derivative. We take C at the end minus C at the beginning and divide by those two numbers. Subtract. Changing Y over changing X, changing C over changing Q. Y'all see, no derivative. Okay? And all we need to do this problem is we need to know what the actual cost function is. The rate of change in the cost in Q is 201 at a specific point. Not over the course of time or over the course of a chain, but right here, right now. What is the rate of change of cost? What am I asking you to do? Yep, that means take a derivative. Find the derivative and plug in 201. Now you can't find the derivative unless I give you the function, but here it is. Does everybody see? Average versus instantaneous. Okay? All right, final thing. Not too much. This seems like a word. Right here. There are some very specific rates of change that we're going to see over and over again. Velocity and acceleration is one. You're going to see velocity and acceleration more than one time. But there are more general rates of change where they just change all the time. You never know what exactly is going to pop up. So, for example, there's a formula that talks about the volume of a cube. Okay, there's a cube, and all the sides are S, whatever that number is. They're all the same thing. And so the volume of that cube is S times S times S, which is S cubed. That's the volume. Okay? So if I ask you to find for me the rate of change, not the average rate, but the rate of change of V with respect to, that's the last time I'm going to write that. With respect to, I'm going to abbreviate this for, okay? Yes? With respect to time. Okay? The rate of change of V with respect to time, I am telling you to take the derivative with respect to time of V.
You try dv/dt.
Yes, this is the same thing as dv/dt. And I am telling you to take the derivative with respect to time of S cubed. Yes? So what am I going to put over there?
The
No, derivative of S cubed,
3s.
3s squared, yes? And then what? Take the derivative with respect to time. Is that T? Stop. Everybody stop and think. Is there something you can't read? With respect to. Okay, so one more time. Okay, D, the derivative with respect to time of V is 1 dv dt. The derivative with respect to time of S cubed, these don't match. So you take the derivative of S cubed, 3s squared, and what do you have to put? ds dt. Right. Alright. You have to pay attention to what you're being asked to take the derivative with respect to. Rate of change of volume with respect to S. Leave them aside. So I'm asking you to take the derivative with respect to S of V and the derivative with respect to S of S cubed. Y'all see the difference in those two things? We touched on this a little bit the other day. Does everybody see the difference? Okay, so how can I write this? dVds. You can also think of it as 1 times dVds. Okay, and then what's the derivative of S cubed? 3s squared. Do I need to put ds on the end of this? No, because that's for body. Okay, so you've got a volume. You might be able to take the derivative in a variety of different ways. You have to be paying attention to which one are they asking for. If I say find the volume when S equals 2, if I ask you to find the volume when S equals 2, then what am I asking you to find? Take V and plug in. That's what I'm asking you to do. I'm not asking you to do a derivative. I'm not asking you to do a slope. I'm just asking you to take volume and plug in 2. Okay? If I say find the rate of change of volume with respect to time, then what am I asking you to find?
What?
No. Well, sort of. Derivative of volume with respect to time. I'm going to put one in here at t equals 4 spread, S equals 2, then you would have to say this right here. And that gets a little bit messier, but it is something that we're going to look at a little later on. I don't think that actually shows up in your home. Okay? All right, let's look at two more little pieces of information that pop up in the workbook. This is not calculus. This right here is just review. Okay, this is not calculus, this is just review. A is proportional to B. What does that mean? A is proportional to B. What can you write down when you see those words? A is, I remember? Proportional to B, where K is some constant. A is inversely proportional to B. Proportional means as one increases, the other increases, or as one decreases, the other decreases. Inversely proportional is one increases, the other one decreases. Does anybody remember what that looks like? That would be 9. It's 1 over. Okay, it's a proportion. Okay, so A over B. Now, some people learn it this way: K equals A times B. This is the way I did both of them. I just want to get it mixed up. Okay, so you just have to watch out for when they change the language on this. So, what if I said A is proportional to the difference between B1 and B2? A is proportional to the difference between B1 and B2.
A equals.
Wait, everybody say something. Okay. Write something down. Oh, wait, write something down. Did everybody write A equals? Did everybody write K? Yes, and times. And then what do I put? The only thing I usually get is people forgetting those things. Okay? So you just have to watch out for what is proportional to what. The rate of change of A with respect to time is inversely proportional to B. The rate of change of A with respect to time is inversely proportional to B. So, what is the rate of change of A with respect to time? The ABC is inversely proportional. A over B. Right? Now, today, of all the days that I've given you notes, I've given you less complete examples than ever before of anything that you're going to have to do. What I've given you is little snippets of things that are going to help you get through all of the questions. All right? And now I'm going to give you back your test. So goodbye, ladies who are listening to this.